Welcome everyone. Good morning, good afternoon, and good evening. Thank you for joining us on behalf of myself and also my co-host, Professor Marco Pavone from Stanford University. Good morning, Marco.
Good morning, everyone.
Welcome to the second edition of our workshop on autonomous and connected transportation systems. The idea of the workshop is to have some discussions on the future of mobility, considering the fact that autonomous vehicles are approaching market readiness and that cyber-physical technologies are kind of entering slowly but very relentlessly the mobility ecosystem. So we want to reason on the implications, on the challenges, on the discussions. And so with this background in mind, basically, we want to answer the questions of how can we design profitable and sustainable mobility systems that leverage these new technologies? What will these new forms of mobility and transportation mean for society? And how can we ensure equity? So how can we ensure that such technologies benefit all members of society, improving equity rather than undermining it? And in this context, the goal of this workshop is to identify the challenges and the opportunities for us as scientists, but also for society, to identify modeling and control methods to address them. And third, to share insights from deployments and turn such insights into an actionable research roadmap. The workshop structure is as follows. The first 1.5 hours, we will have 6 talks by our speakers. And after the presentation, we will have space for a couple of questions, but then we will have also a final half an hour of plenary discussion, which will be moderated by myself and Marco. Having said that, unless Marco, you want to add something?
Nope, I'm good, thank you.
So I would like to introduce our first speaker, Samitha Samaranayake. He's an assistant professor in civil and environmental engineering at Cornell University, but he's also affiliated to operational research and applied math. And today he will talk about how to enable personal mobility for all by integrating public transit with more agile, demand-responsive services, and in this context also about the role of autonomous mobility. Having said that, Samitha, thank you very much for being our icebreaker, and the floor is yours.
Thanks a lot, Mauro and Marco. So I'll jump right into it. So I'm going to focus on the transit-centric viewpoint of autonomous systems and how we can use these emerging technologies to build sustainable and equitable personal mobility. So I want to start with this question of what happens in ride-hailing systems, so non-shared systems that are either autonomous or non-autonomous. We know from existing data that for every passenger mile traveled, about 1.6 vehicle miles traveled are incurred in these systems, in the hailing systems. And this leads to things like increases in all the negative externalities. So for example, congestion and emissions. And I want to actually just illustrate this to a quick video. This is actually some work that Marco and others did a number of years ago. So they took the travel data from Singapore for 800,000 passenger vehicles and then tried to say what would happen if you serve this with 300,000 shared autonomous taxis. So this is a map of Singapore. You have these red stationary dots that are stations, blue dots that are moving vehicles with passengers on board, red dots are empty vehicles. These disks that are growing, the bigger the disk, the longer the waiting time. So, people are waiting in the suburbs in the morning to get a ride back to downtown. During the middle of the day, activity is kind of balanced. There's a lot of movement, not much waiting, reasonable amount of rebalancing, not much. Now we're hitting the evening rush hour, and you'll notice that people will start waiting in the industrial and business districts, and streams of red dots will move. People are waiting for them to come, the vehicles to come, they get picked up and sent back home, right? So, what's happening here compared to driving your own personal vehicle is all of these red dots that were moving, they would not be in this simulation if you were driving your own vehicle, right? So fewer vehicles are needed, but those fewer vehicles are driving a lot more. Okay, so another important thing here is that when you have competing service providers, let's say Uber competing with Lyft, this fragments the market, and this fragmentation leads to even greater inefficiency in the requirement for rebalancing and deadheading. So this is a challenge. So, just having ride-hailing systems are not better than us driving our own vehicles. And the question now also arises, well, can autonomy help? Does autonomous ride-hailing, is it better than regular ride-hailing? Yes, to some extent, because you have centralized control and get more efficiency, but fundamentally you cannot eliminate the need for rebalancing, and this will introduce inefficiencies. So the question is, what can we do with these technologies that are more scalable and sustainable? There are three kind of obvious steps we can take. One is to encourage and enable true ride sharing, so high capacity nodes, think of Uber Pool, microtransit, even completely shared autonomous buses. Feeder systems to mass transit. So these are things that you take a shuttle to transit station, for example. And then finally, completely rethinking from the ground up public transit in the context of these different modes that are available. So fixed line, traditional transit, working seamlessly with demand responsive services. Very quickly at a high level, these on-demand services usually are operationally managed in the following multi-step process. First, you go on an app, make a request. The request goes into the operator's system. The operator then comes up with some potential configurations with people can share trips. This is done through some tools, and you create what is called trip configuration list. And once you have this trip configuration list, you solve the assignment problem, which is typically an integer linear program, to assign people to the vehicles. And once you solve this problem, you get a solution, which is the assignment of requested vehicles. And this is typically done by aggregating demands over a, let's say, 5 to 30 second period to increase the efficiencies instead of greedily assigning requests as they come into the system. Okay, so this pipeline needs to be therefore solved very quickly. So again, in the order of 5 to 30 seconds, you need to solve this optimization problem. And there's a lot of research in this area. So again, to illustrate what this would look like, here's an example. Here's an example from taking all the taxi demand in New York City. So for a given day, it could be 400 to 450,000 trips served in the real world by 13,500 taxis. The question is, what would happen if you were to now serve this using, let's say, 1,000 shuttles, right? So again, a short video. Each of these dots here, the color of the dot represents the number of people on board. So a capacity of up to 10. Dark blue vehicles are empty vehicles rebalancing. So rebalancing doesn't go away, still it might be necessary. In this case, there are 1,000 vehicles, capacity 10, a maximum waiting time for 7 minutes and V2 of 14 minutes. And we can measure service parameters like the service rate, waiting time, in-car delay, occupancy, etc. And here you see there are two trajectories, the green and the blue. These are two of these 1,000 vehicles, and every 30 seconds they're being rerouted to pick up and drop off people, and the route is changing dynamically. Now, we can also look at what happens when you have different capacity sizes. So in this case, now we have the same example, capacity 1 taxis, capacity 4 vehicles. You can think of this like a Uber Pool car, and capacity 10 shuttles. And what's interesting to see is how, again, what the trend is in terms of the performance metrics. So when you have single capacity vehicles, the service rate is the lowest. So in this case, we get a service rate on the order of 50%, whereas for the capacity 4 vehicles, it gets in the lower 90s, and for capacity 10, it's in the upper 90s. The waiting time also decreases as the capacity of the vehicle increases, and this is because the increased capacity means that there is an increased effective fleet size, right? There are more spots in vehicles to move people, so you have to wait less time. Of course, there is a trade-off. The in-car delay is 0 when you are taking a taxi. You don't have to share it with anyone, and you don't get to be detoured. And when you increase the capacity of the vehicle, you need to spend more time on the vehicle compared to a direct trip. Another really important thing here is that the travel distance. So the travel distance is decreasing as you increase the vehicle capacity, and it's serving more people, right? So what this really means is that we're getting great savings in the ratio between passenger miles traveled to vehicle miles traveled. Okay, so so this is in the context of end-to-end services. There's been a big push in the US, at least, in trying to explore this idea of demand responsive public transit, and particularly in the context of what's called microtransit. Small shuttles that mostly are getting people from their origins to some kind of transit hub, to first last mile connectivity, and in some cases as an end-to-end service. So why is this useful? Here's an example of a motivating example from the Seattle area. So King County Metro is one of our research partners that operates the public transit service in the Seattle region. This is a picture from one of the park and ride stations called Northgate. So this location has about 1,350 parking spots. And people come and park their cars there and then take some kind of rapid transit service to downtown Seattle. Now, what you can see here is that the utilization is 98.5%. So this includes Christmas and New Year's. So which means this really means is that the parking spots are completely full every day. Right? So if you don't get there in time, you might not have a parking spot and you might have to drive. Now, what they would really like to do is not to increase the parking availability in these stations, but to in fact get rid of them and find other means by which people can get to transit hubs and increase transit utilization. So one use case would be to use dynamic shuttles, shared shuttles to bring people to these kinds of park and ride stations. Now, in the context of the operational optimization, what this means is that now you have to come up with trip configurations, possible routes for moving people in that correspond to this demand profile. It turns out that transit-centric problems lead to much larger problem instances than the problem instances you see in the TNC setting. And this is because in the transit context, we typically have reduced quality of service constraints. People don't expect the same high quality, low waiting times and low detour times as you do with the taxi service, for which you're typically paid much more. You have larger capacity vehicles and you have advanced bookings. All of these things actually lead to a more complicated optimization problem. And just to give you a flavor of that, if you look at the example from New York City, so the shareability graph is a compatibility graph that tells us which requests can be shared with each other. In the case of the Manhattan example, even with 450,000 requests and the capacity 10 vehicles, at each given instance of the problem, the number of feasible trips is on the order of 3,000 to 5,000. If you look at a much smaller, a problem that seems much smaller, this school bus routing problem, where now there are 403 students who need to be moved to a school in buses of capacity 72, even with some minimal pruning, the configuration number of possible feasible configurations can be as large as 8 to 10 million. Okay, so this is a huge increase in the size of the problem, even though the problem seems to be a smaller problem than what we looked at in the Manhattan context. Okay, so this requires techniques of search pruning and clever optimization techniques to be able to solve these problems in real time. I also want to talk a little bit about the challenges here that are perhaps non-technical. So the early instantiations of these microtransit pilots were all failures. So the first big experiment was one with Bridge in Kansas City. It was a complete failure. In a whole year, there were about 1,500 trips that were serviced by this system. Chariot was another player in this market that Ford bought a couple of years ago, but then shut down its service. So they were not profitable. The question is, so what's going on here? One of the major limiting factors is that in transit systems, a lot of the operating costs has to do with labor. So this is a comment from Jared Walker, who is one of the leading transit consultants. Driver labor and related time-based costs are the dominant element, often 70% of more of transit budgets. Okay, so running many smaller shuttles is not cheaper than running a few huge buses. And this is really, and TNCs actually can get around this because TNCs operate at a lower cost than transit agency due to labor laws. So if you don't have to pay a union wage for the TNC pilots. So a lot of microtransit pilots that have been successful have been operated by TNCs for this reason. But this provides really an opportunity for autonomous vehicles to change the equation of the economics here and make it more likely that these kinds of solutions, multimodal transit solutions, could be economically viable. I'm going to finish off by making a quick note of what I would say is sort of the holy grail of this line of thinking is fully integrated hybrid transit systems. In transit planning, it's well understood that if you want to maximize ridership, that you should operate a few routes at very high frequency. So if you look at the lower right, the two images in the lower right, if you want to maximize ridership in this hypothetical city, you would run all your buses on these two routes where there's a high density. But of course, a large number of the community would not have easy access to transit. As in the maximum coverage solution, you would run buses everywhere, but they would run at very low frequency, which would mean it was a much more inferior product for people who are using it, and therefore fewer people would take it. And many cities have, because of this and the need to increase ridership, gone to more ridership-based transit planning strategies, which means there's equity considerations. The question is, can autonomous vehicles and new technologies get a better balance between coverage and ridership? I will stop with that with finally a plug for a workshop that's happening at IPAM in November that is very related to the questions that we are talking about in this workshop, and many of the speakers will be participants as well. Thank you very much.
Thank you, Samitha. Very interesting. You can stop sharing your screen. Whilst I ask Milos if you can start sharing yours.
Yeah. Do you see the screen?
Yes. So let me introduce you. Milos Balac is a postdoctoral research scientist at the Institute of Transport Planning at ETH Zürich, and today he will talk about the shared autonomous on-demand services and the analysis he has carried out, especially for the city of Zürich. So Milos, thanks a lot for participating, and the stage is yours.
Sure. Thank you for the invitation. Thank you for the presentation, and thank you, Samitha, for breaking the ice. So I will be talking about mostly about our framework for modeling the demand for shared autonomous on-demand services. So let me just see. Okay, so usually when we have some operational decisions to make for the AV fleet, we usually consider demand static, and this is usually the reason behind this is either we want to isolate the problem or maybe the lack of data. And then as in this case, for instance, we want to vary the fleet size, and when we want to look at certain KPIs of the AV fleets, as in this case, the waiting time. As here we see, for instance, as the fleet is increasing, of course, the waiting time decreases in this case. However, as you might imagine, the impact that we have on the operational side also has impacts on the demand. So our demand curve is actually dynamic and looks probably more like this. And the question that we are raising is, how can we model this dynamic demand? So we need three things. One is the behavioral model, which explains the trade-offs that individuals make between different transportation services. We need to know what is the cost of different transportation options available to the individuals, and among them the AV service. We need a simulation framework where we can test different operational decisions or different policies and their impacts on the behavior of the individuals in the study area. So in order to obtain the behavioral model, the city of Zurich, we conducted a stated preference automated vehicle survey where individuals had to trade off between different transportation options, among them different automated services as well. Then the potential cost of automated vehicles was also estimated based on different regions and also for different kinds of modes. I don't want to go specifically into any of these numbers because they're not so much important for what I'm saying later, but these little pieces of work are important for the final complete simulation framework. So the framework uses a multi-agent transportation simulation, which simulates individuals and their daily plans, and also their interactions with the transportation system. So you can imagine also their interaction with different AV fleets, which is important when we want to look at different operational decisions. Now, the MATSIM framework takes into account, has a discrete mode choice extension, which takes into account these trade-offs that people make when they're performing trips. And also we take into account the changes or estimation of the costs for the AV fleets based on utilization, fleet, empty distance, waiting times, fleet size, and so on. This is an iterative approach that equilibrates in the end. Now, I want to show you a couple of studies with this framework and how the study can help us to understand how different policies can impact the shared automated services. So the first one is on single occupancy AV taxi demand in Paris. So we look at the city of Paris, where we have 2.4 million trips that are potential trips for AV service. We consider mode choice and we consider the costs for the AV services. We look at the static price, free static prices between 0.15 euros per kilometer and 0.45. But we also look what happens if we take into account that this price is actually dependent on the fleet size and the utilization of the fleet. And this is this dynamic demand that we were hoping to see from the beginning of the presentation. And this is what we actually find out in the simulation. Here we can actually see that the optimal price where the highest demand is around 0.3 euros per kilometer, and demand is around 1.2 million trips. Now, what is important here is that this optimal price is very close to the marginal cost of car ownership. So you can imagine that this service is actually very, very attractive. What is not good is that currently the modal share of car trips in the city of Paris is around 10%, which means that with more than 50% of trips done by EMO, by automated mobility on demand service, can bring a huge shift to car travel, which can cause quite considerable negative effects. That's why the reason is another reason for us to really put a lot of effort into designing policies that will shape the usage of AVs. Now, I want to show you another study that we've done for the city of Zürich, where we looked at automated transit on-demand service. So we split the area in hexagonal zones. We consider each centroid as a potential pickup and drop-off location, so each centroid of each of the zones. So the individuals can travel from each centroid to each other centroid. There are no detours, and the service has a defined frequency. So it's a kind of a hybrid public transport service. What we look at is no mode choice, no cost constraints for the usage of the service, and we want to replace all car trips. And then we use optimization algorithm to minimize the fleet size and the vehicle kilometers traveled for this service. What we find out is that without pooling, the necessary fleet to serve the demand is around 11 to 18 times smaller than the current fleet size, depending on, of course, the characteristics of the service. However, we have an increase of the VKT between 3 and 24%, which is, of course, undesirable. If we have a maximum 2-person pooling triggered, we even further can reduce the fleet by a factor of 20, and we can also slightly reduce the VKT. Finally, if we use a mixed fleet, which is in this case 2, 5, and 10 seaters, the fleet can be reduced by a factor of 27. More importantly, the VKT also drops by up to 10%, which is a quite nice result. But now we want to use the framework that we proposed. We want to use the mode choice extension. We want to take into account waiting times, travel times, the costs. And then we again want to optimize, actually to minimize the fleet size and the VKT for this kind of service. I'm going to show you here two scenarios. One scenario is where we allow the service as before to be used in the whole area. And the second one, again, the whole area can be utilized. However, we price more the zones where the accessibility for public transport services is very high. So in this way, we want to protect the public transport service from this kind of automated transit on demand service. And these are the results. So in the scenario one, with pooling and a mixed fleet, we actually only have a vehicle replacement rate of 4:1, so considerably lower than what we expect in this corner best scenario case. We also have a VKT increase of 6%. The total fleet reduction in the whole scenario is around 16% when we consider both conventional cars and the AV vehicles. Here, the A2D service had a modal share of 24%. Quite high share, not only taking away the car trips, but also public transport and cycling trips were now replaced by this service, which of course is something that we don't like to see. So in the scenario two, if we protect the areas with high PT accessibility, we can achieve actually lower vehicle replacement rate of only 10:3, and VKT increases by 5%. The reason why the vehicle replacement rate in this case is lower is that the actual demand, the highest demand, is actually in these areas where the PT accessibility is high. So because of this, the possibilities for pooling that we are observing in these scenarios is actually, in this second scenario, is actually very low. So we see that we urgently need to think about policies that we are going to have in the world of AVs. And our hope is that this proposed framework that I've shown you here can actually help us to better understand the impacts of those policies and also different operational decisions for the management of AV fleets. Is it the fleet size? Is it dispatching, relocation, and so on? Thank you. Questions?
Thank you. Thank you, Milos, for the very interesting talk. Are there any questions from the audience?
Hey, Milos, I have a question. Great talk, by the way.
Thanks.
So it's Marco. I was wondering, for your pricing scheme, does it rely mostly on trial and error, or is the result of an optimization process or something similar?
So basically, it is kind of an optimization process. So basically, it goes into this iterative loop around. It's an external plugin which takes into account the utilization of the fleet. How often are these vehicles used? What is the pooling ratio? And then takes into account this variable in order to calculate the cost in the following iteration in order to provide a marginal profit for the service. So it always maintains this marginal small profit for the service.
Got it. Thank you.
Sure.
We have a question by Cara. When do you think many individuals can start renting shared autonomous vehicles and then buying AVs in Switzerland? And what is the long-term price difference you are assuming between a vehicle that is conventional versus a vehicle that is fully automated?
Sorry, yeah, can you maybe repeat?
Yes. So when do you think many individuals can start renting shared autonomous vehicles and then buying autonomous vehicles in Switzerland?
Yeah, I think we are actually quite far from there. But this gives us actually time to design these policies and to think about the various impacts these policies can make on our cities. The long price difference, yeah, so basically we are taking into account the cost estimates that were proposed by Patrick Bush and also that were used, that were done for the international cost calculator, which you are a part of. So yeah, so basically for the conventional vehicles, we take into account current cost estimates, and for the fully automated, we take what is calculated based on this methodology by Patrick Bush.
Okay. Thank you, Milos, for your talk. So now I can introduce the next speaker. Carlos, you can start sharing your screen if you like.
Yeah, can you see it?
Yes, perfect.
Okay.
So let me quickly introduce you. So Carlos Lima is associate professor at the Technical University of Denmark, and he's also a research affiliate at the ITS lab of MIT. And today he'll discuss the impact of AMOD implementation policies on demand, congestion, energy, and emissions for different urban typologies. Thank you very much for joining us, and the stage is yours.
Okay, thanks, Mauro, and thanks everyone for joining. I'll follow up, I think, in the same line as Milos, previous presentation, and hopefully set the ground also for Kara, which is interesting, at least from the abstract. So I'll jump quickly on a recall of what Mauro suggested initially to us about what we should be trying to provide a path towards. So, and what I wanted just to add is some of us actually have the same question, but even more dramatic, which if the previous questions for AVs, so how can we design profitable and sustainable mobility system that leverage AVs, and how do we make it available for improving equity rather than undermining it. So it's challenging, and trust me, all of us, we have this in our minds for general, not just AVs, which it's even more difficult, and that's probably the nicest word I can say. But so that was the purpose, the initial purpose of building up C-Mobility. So again, it falls into this set of tools, simulation tools, for answering most of these questions for future mobility scenarios. So a large portfolio of solutions. So it integrates a modular agent-based code and algorithms. The key or most interesting aspect of the C-Mobility platform is the fact that the behavioral models that are integrated along with network models are quite advanced. And a couple of years ago, it has been made open source, so that becomes much more attractive to the whole aspect. So I'll just briefly explain what actually happens in C-Mobility midterm. So it's called midterm because the long-term focuses on land use and long-term choices, and I'll come back to it a little bit at the end of this chat. The short term, on the other hand, you can think as a microscopic traffic simulation model, so much more detailed supply simulation. The core of the midterm, though, it's this integrated simulation of demand and supply, where you basically have a population and land use that generates then plans for the day. So it's an activity-based model, which is called the pre-day. And then the simulation kicks in, and we have again, demand models in a loop with the simulation of the networks. And here we have road networks, and we have rail networks, and then we have controllers for simulating the operations of different mobility services. So you can think about the bus controller, the rail controller, then mobility on demand controllers, and we have multiple of them. And it will be the same case for autonomous mobility on demand. So you'll see along the presentation, so I don't want you to focus too much on the top side of this slide, mostly on the bottom side, but I know you'll have a hand on the slides. So basically at the end, I have all the details about publications that I'm referring to here. But the story of C-mobility and the study of automated mobility started back in 2014 with the quite renowned paper by the MIT folks in Singapore, where they looked at the problem of fleet sizing. And then basically we noticed that, okay, this of course will have the problems of changes in demand and in congestion, and that's where C-mobility came into play. And the first studies initially looking into congestion and extended the fleet sizing problem with mixed fleet and different types of services. And on the demand side, as soon as you get different types of services that the operator provides, and such as single ride and shared ride, then you should allow on the demand side to users to choose. And so there was started to look at shifts into multimodality a year later. And on the supply side, the rebalancing algorithms came into play. So this was back in 2018. I would say in 2017, some basic algorithmic scheduling and matching were implemented and started to play around. And there's plenty of room to play around with those, especially from the OR folks that are interested in doing it. And then in 2018, a set of developments on the demand side started to kick in. So that's transit integration. The Boston case study appeared as well. So that's the greater Boston area, along with energy and emissions. And last year, basically we tried, and the team tried to rely a lot more on data from preferences on AVs, so similar to stated preference services, but context-based, so we could rely exactly on trips that people have done and try to put them in that context related to AVs. And then also looking at this year on accessibility-based measures for looking at the impact on equity and on the demand itself, and then on longer-term choices as residential choice and vehicle ownership. So that's basically the summary. And one of the recent studies that ended earlier this year was on looking at not so much on a specific city like Singapore, Boston, or previously Zurich or Paris, but trying to see these usually simulation exercises require a lot of data, require a lot of detailed calibration to make sure that we get the perfect city into our model. Then the detailed scenarios so that it matches with the current situation of the urban environment that we are considering. And of course, then the detailed outputs because we are looking at a particular city. And usually the questions of transferability arises on how much of the insights that we get from this exercise can be looked into other cities. So kind of this motivated us a while back to look at typologies of cities instead of specific cities. And would it be possible to still use the same framework on simulation, but this time on prototypical cities? So here we had to identify urban prototypes, then build those prototypes in a simulation model, do our autonomous vehicle scenarios, and then look at the results. So this was a study with the MIT Energy Initiative. And there's the link up there in the slide if you are more interested. Actually, there's a report that came out earlier this year, which is, I recommend everyone to read on future mobility scenarios from across the board. So the exercise on finding urban typologies, we collected data for 331 cities. So this was open data sets, and the actual full data set is available in the link there, which is open again. We had around 64 variables for each of these 331 cities related to mobility, economy, environment, social development, urban form, and geography. So even we scraped OpenStreetMaps to get indicators about the topology of the networks for each of those cities. Alongside with it, then we have not open data, but there was a survey that was running in a subset of these cities to a total of 18,000 individuals, and where very brief survey, I can say, where only a few questions were asked them on how they perceived AVs and when would they be ready to be safely used in their specific cities. And people were asked just to rank on these perception indicators. And this was along with social demographic variables that were asked to individuals and other questions on other technologies related to mobility. Then what we did was we did a factor analysis and then a clustering, and we came out with 12 typologies using the first data set. And then we kind of did a confirmatory step where we checked with the behavior data from the surveys if any city would fall under a different typology. So this is kind of the map of the 12 typologies around the world. Of course, we could come out with not 12, but a different number. And so again, this factor analysis and clustering have some, let's say, subjective judgment when doing it. I'm not sure I'm using the right word, but basically this was what we think was the best one represented from our data set. And we then picked 3 typologies to actually do the exercise of the simulation and AV scenarios. So we picked the auto-innovative and auto-sprawl, which are mostly North America, Australia, and some Middle Eastern cities, and the mass transit heavyweight, which are also available. We can observe them in North America, but also quite spread in Asia and in Europe. So how these cities are characterized by, so here we have the 9 factors. At the top and at the bottom is more tractable data that you can, out of the 64 indicators, so you can see mode shares for car, mass transit and walk, and the population density for these types of cities, and also the production of CO2 per inhabitant, and some examples at the bottom of what these 3 typologies are. So then we've generated these 5 scenarios, so the base case, and that's as is. Then we introduced AMOD, both single and shared, and we assumed that the fare is 50% of what the current mobility on demand services or TNCs available in 2016. Then we had another scenario, which is AMOD without public transit. So this is the scenario where we say, okay, public transit, we just get rid of it, and now let's see if AMOD can replace it. Again, just a scenario. Of course, we only simulated for auto-sprawl and auto-innovative cities because the dense transit heavyweight have a huge share of public transit trips, and removing it would be not a good idea. On the other hand, we had also AMOD and transit integration. So here, the MOD would be restricted to local trips, and there would be a 20% discount to access and egress to mass transit. And to replace this AMOD no transit, we had a scenario just for the mass transit heavyweight, where we had a car reduction in households of 25%. And the results that we get, and I'll speed up to just 1 more minute, we had mode shares that we've computed for all scenarios. And I'll try probably to speed these 3 slides, and these are in the papers. But basically, we did mode shares analysis in this presentation, VKTs and congestion, so travel time index that was computed, but I have here summarized just for you, so to speed up. But in all scenarios, basically, we had AMOD eating up to 20% of mass transit, all scenarios except the one without integration. There was an increase of VKT up to 30% and a congestion up to 50%, and all scenarios had an increase in congestion, and that's a bit similar to what Milos was pointing at. Energy and emission impacts are city dependent, and again, this was heavily dependent on the fleet composition of electric vehicles. And in general, AMOD cannot substitute mass transit in dense cities. So what we are looking into now is basically adding detailed preference from surveys that appear in a couple of cities and that we have done in Boston and in Singapore. We are adding accessibility-based measures for consumer surplus and for welfare calculations for all these scenarios. and the team at MIT from urban planning is looking at long-term choices. So in summary, the study was then focused mainly on the MIT side and Singapore by the team at the top, and currently looking at usage of C-mobility for SAV-related studies. We have an increasingly number of teams joining the party, so we hope that this sets the ground for a few more to join in. So that's it.
Thank you, Carlos, for the very interesting presentation. Perhaps we have space for one question? Yes, by Cara. I imagine the single best policy we can adopt here is credit-based congestion pricing, where revenues go back to residents and can be used for all sorts of modes. Any thought?
Yes, I do. So could be. So that's purely on a demand management policy, and it's the difficulty on those schemes is exactly identifying in practice how they would work. So of course, they should match congestion pricing as much as possible with all the benefits from welfare distribution, but it's always a matter of what in practice can actually be done in such schemes. And so when and how do you adjust the prices, how you would distribute the credits, and eventually should the autonomous system take some of the decisions on how to manage them, or should you leave it on the demand side and on the individuals to take the lead on it? So those questions are, I think, the community is getting a little bit more interested in that topic, which is I'm also, and hopefully there will be some answers to this problem in the near future.
Okay, thanks a lot. I think we need to move on. Thanks a lot for the very interesting talk. So it's Christos' turn. Christos, perhaps I can ask you to start sharing your screen.
Yeah, I'm here. I'm ready to go.
Good. So Christos Cassandras, he's a distinguished professor at Boston University, and he's also the head of the division of systems engineering there. And today he'll talk is a very fascinating title about the Internet of Cars, and specifically a decentralized optimization framework. Christos, thanks a lot for joining us, and the floor is yours.
Thank you. So I'm going to put more emphasis here on the technological side of how can we get the so-called Internet of Cars using autonomous vehicles to work. So I don't think I need to motivate very much the need for controlling traffic because of congestion phenomena that occur all over the world. And I can perhaps motivate the need for autonomous vehicles by asking this question of why has it been so difficult for us to control traffic networks? And I propose two basic answers to that question. The first is that we just don't have the ability to control traffic networks to the point where we can unleash the power of feedback from control theory and engineering. The second is more a game theoretic point of view, because we are players in a game as drivers in which we do not share information, that results into poor decisions. That's a well-known game theoretic fact. And that also leads to this gap between the individual selfish optimum and the system-wide social optimum, leading to the so-called price of anarchy. And this motivates the need for connected autonomous vehicles, the ability to actually overcome this inability to bridge the gap between selfish and socially optimal behavior. And if we had the ability to automate every single vehicle on the road, but we can't, but at least a fraction of that, then would obtain what we call the Internet of Cars. So how can we develop these CAVs, and do we have the technology to achieve this automation and communication? So I start with this picture here that shows the test bed referred to as M-City. It's located at the University of Michigan campus. You see a real picture on the left that gives you a sense of the size of it. It's not terribly large, but the interesting thing about it is that it contains all the features that one might encounter in a city and also in a slightly suburban area. So you see a stretch of a highway here, which is what you see in the real picture over there. And in fact, we have, as part of a team, an automated vehicle, which we call the Next Car. And we are playing all sorts of games, testing this technology at this MCD testbed. So if you look at this testbed, it helps you identify the key congestion points, the conflict areas where you really need to apply some control. And I show here, for example, an intersection, a merging point, or a stretch of a highway where you have all these lane changing maneuvers where conflicts arise as well. So if we were to focus on all these points, we can define so-called control zones within which the vehicles cooperate to achieve good desirable performance. And from an optimization standpoint, we need to identify criteria, which, as best as I can tell, include travel time, energy, passenger comfort, and of course, and perhaps the most important thing, safety, which I'm going to focus on in this talk. How can we not only achieve the optimization criteria here, but guarantee safety? So from a technical standpoint, if you focus, for example, on a merging point, which I'm going to give you a little bit more details on as an example, you formulate a problem like this, where the important thing is to focus that there are three components to this objective function: travel, energy, and comfort. What we're controlling here is the acceleration, or indirectly the speed of the car. And you see here that we have the various constraints of the optimization problem, which includes the safety constraints that I show here. And what is important is that for any one of those control zones in the traffic network, we can define such optimization problems and solve them. This is just a snapshot of work that has been done in this issue of vehicle coordination. I'm not going to go in detail. I just want to call your attention to the fact that most of this work has been done over the last 10 years, and it falls into two categories: centralized and decentralized approaches. The approach that we are following is a decentralized one. So I'll give you a quick overview of how you apply this decentralized optimization framework in the merging problem. This is a picture of the merging problem. It can get pretty complicated, but you can see that we have vehicles that come from what you can think of as the main highway, and then vehicles that come from the side ramp, and they merge here. So there's a merging point. The dynamics that we assume are fairly simple, and the interesting quantity that I want to point out is that the distance between a vehicle and the one right ahead of it is important because it prevents collisions. So in terms of safety, we have this particular safety constraint that involves the relative distance, as in this example, between vehicles 2 and 3, which is speed dependent. And there is a parameter which is typically taken to be around 2, 1.8, which has to do with the headway. And then you have, of course, the other safe merging constraint criterion, which again relates to a speed constraint of this form. So the optimization problem, if you were to solve this merging control problem, fits in the framework that I just showed you. We want to minimize both travel time and energy. And all I want to show you from a technical standpoint is that if there are no active constraints, which is not true, most of the time there are, but if there were no active constraints, the solution is actually pretty simple. You can see here it turns out into polynomials in control, speed, position, and the two cases that you need to analyze are the cases where you have two successive vehicles. Here I'm assuming that there's a first in, first out order inside the control zone, so that, for example, vehicle 3 and vehicle 4 should preserve that order. So depending on whether the vehicle ahead of you is in the same lane as you or not, you have these two cases that you have to analyze. This is a little simulation that shows you what happens when you apply this optimization framework to a merging problem. This is, of course, just simply a toy example. the thing to notice is that you see that sometimes some of these vehicles accelerate or decelerate to fit in. If you see a blue vehicle every once in a while, this is to show you that you don't have to stick to this first in, first out constraining criterion. So what you do is you reorder vehicles. Whenever you see a blue one, it turns out that it's one that we reorder to make more sense of this problem. And if you focus just on this red circle here or oval, you can see that roughly, depending on whether you pay more attention to energy or travel time, roughly compared to the human-driven vehicles simulated under a standard simulation package called VISIM, our approach, the optimal control approach, essentially improves the average objective, a combination of time and energy, by a factor of 2. So it's a significant improvement. But this is what I want to focus on now. Going from this nice, clean, optimal control framework to execution is a big step. Once you get into the real-time execution of this type of technology, then you have to face issues like uncertainties, noise that creeps in, the more complicated non-linearities that vehicles exhibit, as opposed to the more idealized sort of double integrator model. And the way to achieve this optimal, without losing too much optimality, because you will lose some, but the way to achieve safety with losing minimal optimality is possible through what we call the control barrier function approach. So to put things in perspective, I'm comparing here the pure optimal control setting, in which the main advantage, of course, is to achieve optimality, according to the criteria that I talked about, travel, energy, and so on. But the disadvantages are that once you get away from fairly simple models and you have a lot of constraints to deal with, things can become complicated in the sense primarily of time consumption. So I am advocating a decentralized framework. All this has to be solved by a processor which is on board your car. That becomes difficult. A popular way to overcome this problem or to apply optimal control solutions in practice is so-called model predictive control, MPC. The advantage is that it becomes easy to solve in real time. The disadvantages are that it's suboptimal and there are linearization errors, and you cannot always guarantee the safety that we would like. So here's an alternative, which is based on so-called control barrier functions. The advantages here are that, again, it's easy to solve numerically. It has a fundamental property called forward invariance. That's very important, because what this guarantees is that if you start out being feasible and enforcing all of your safety constraints, you remain feasible in time as you move forward. It can accommodate nonlinearities and fairly complicated constraints. It also allows us to make our objective functions more complicated if we so wish, and it can accommodate noise. The disadvantage, like MPC, is that I can no longer guarantee full optimality, but as we have been getting results, the suboptimality is minimal. This is just a very, very quick technical overview of the CBF approach. The idea from a control theoretic perspective is to start out with system dynamics that, as you can see, are nonlinear, but they're affine in control. So I'm not bound to the simple linear models that I presented under the optimal control approach. A control barrier function must be a continuously differentiable state constraint function that generally looks like this. So it's whatever the constraint is that you're interested in. The idea of the CBF approach is to map the state-based constraints onto constraints that depend entirely on the control input. And when you do that, the constraint that you see here becomes something like this, which looks more complicated, of course, but it's not really that complicated. To clarify things, these L's that you see here are Lie derivatives. So they are derivatives that you take for your constraint, but along the lines of this dynamics that we have here. And the last term here, the gamma, is any so-called class K function. It's just a strictly increasing function that starts at 0 and goes to infinity as t goes to infinity. So a simple linear function would be fine. You could just think of this as just the original constraint that you start out with. That's all I really want to say about what the CBF does. The key thing is that it maps the state constraints onto control exclusive constraints. So that's a very nice advantage. Plus it guarantees this forward invariance. So here's what, and this is really my last slide to just show you what you can accomplish with the so-called OCBF approach, the combination of optimal control and control barrier functions to sort of output the benefits of both with minimal loss of optimality. The optimal control solution becomes an input to this controller. Now, what do I mean by the optimal control solution? The simplest possible form that you can deal with, the unconstrained case, which in almost all cases that we have looked at is fairly easy to obtain. In fact, if you can convince me that you can get in under a second, let's say, an optimal control solution for a more complicated model, so much the better. Just feed that to this controller. The other thing that is fed into that controller are the rear end safety constraints, collision avoidance, the safe merging constraints, again, collision avoidance, vehicle limitations like limits on speeds and acceleration. And in addition, you can change the simple linear dynamics into nonlinear dynamics. You can include nonlinear constraints, not just simple linear constraints like the distance between two cars has to be greater than or equal to something. You can make your objective functions more complicated. For example, people have always commented on the fact that we use very simple energy functions, fuel consumption functions, and it's true. But if you adopt this approach, you can use your favorite fairly complicated energy model, which can be very nonlinear and quite complicated, and that does not really pose a problem. You can include noise. So your vehicles may be subject to noise, your measurements may be subject to noise, and at the output side, what you do is you essentially develop an optimal tracking solution of a desirable optimal control solution, which is sort of the ideal case, which you know can never really be achieved. But you try to get as close as possible to this desirable optimal solution without violating any of your safety guarantees. So the open questions that remain are what fraction of connected autonomous vehicles does it take to realize the benefits of this approach? Well, that's a very interesting question. Is it 10% or do we need to go to 95% before we can realize the benefits? How do we integrate cabs with pedestrians, bicycles, and so on? I mean, I'm promoting this idea of full automation of a vehicle. Yeah, but you know, vehicles are not the only things on the road. There are also pedestrians, bicycles, and so on. Then, as we heard from some of the previous speakers, there's the idea of moving into a model of shared, I see that my time is over. I think that's a very desirable direction, especially if you consider this statistic that as private owners of cars, the utilization of our cars is only 4%. So I'm a big advocate of mobility on demand. And I'll just stop there. I will take any questions, and I don't want to take any more of your time.
Thank you. Thank you. We have a question We have a question by Carlos, 2 in 1. How is the optimal control barrier function extendable to a network of control points, especially in larger urban settings? Then, for instance, closed sequence of mergers, sequence of intersections, and so on and so forth. And is it far from practice? Is the technology still focused on the local problem, or what's your view?
Yeah, so that's a very reasonable question. So far, our work has focused on separate conflict areas, like what's happening in the highway, where we're worried about automated merging and splitting maneuvers. what happens at different intersections. Let's think of intersections because those are the cases that pose the most interesting connectivity problems, coupling problems. So yes, it is possible to extend this sort of approach to a network, let's say, of intersections. In between intersections, typically you have areas where the two intersections are decoupled, so you switch back into a non-autonomous mobility mode. The cars relinquish control back to the drivers if you so wish. But what happens if you have intersections that are very close to each other? Then we're working on that right now. And of course, what you would like to do is you would like to know, for example, what's happening in the downstream intersection so that you can control the upstream intersection better and not just optimize the flow there only to find out that 3 minutes later, you're creating congestion downstream. It's possible to do that. It's computationally, it's not like things are exploding. It's not like you have an exponential explosion of the problem. But all I can say at this point is that we're working on it, and I think that there is light at the end of the tunnel.
Okay, thanks a lot, Christos. So let me then introduce our next speaker. Cara, I see you're already sharing your screen. Perfect. So Cara Kockelman, she's a professor of civil, architectural, and environmental engineering at the University of Texas at Austin. And today she'll present some large-scale simulations for shared autonomous vehicles, considering geofences, stop aggregations, parking restrictions. I'm looking forward very much to your presentation, and thank you for joining us. The stage is yours.
Thank you. Yeah, we're glad you organized this session. It's not often that all of us get to be in the same session together. So I'm going to talk to you about 3 different papers, and the first looks at the Chicago region, which is that image you see on the right, and that's a very big region, about 11 million people. And then we shift to a small region so that we can simulate absolutely 100% of people, and we also push that population up to make it look like downtown Chicago. And then finally, we shift to the Minneapolis-St. Paul region. So all 3 of these regions are in the US, and 2 of them are in Illinois. And Murti Gudamurti helped prepare the slides, but Hanan and Josh, who's at Argonne National Lab, also are co-authors on at least one of the following papers. So the 4 geofences in the Chicago region, we didn't, I guess, just look at the CBD because it's mostly jobs there. So there wasn't a lot of interesting trip making, but we just took the city of Chicago, which is in pink. And there's so many jobs in the city of Chicago, but most of the zones have a very heavy population share because the jobs are in just a subset of zones. So you get a population to jobs ratio when you average across the zones, that's quite high. And it's even higher if you pull in the rest of those zones for this, I guess, 20 county region with about 11 million people. And so serving that is obviously a lot harder. I think we simulated about 50% of the person trips, and they were allowed to choose other modes. So only about 7% of the people in these different regions were choosing the SAV mode. And we wanted to see how operations like response times and empty vehicle miles traveled varied depending on the geofence. So when there is a geofence, both the origin and the destination have to be within that fence. Otherwise, you've got to choose a different mode. And one thing that was interesting to me that I've been wanting to get a sense of for a while now is the wait time by location. So depending on where your origin is. And so these are images of the whole region on the left here. This is 20 counties, 11 million people. And you're seeing, of course, near these boundaries where SAVs can't go any further than this, you're seeing some pretty high response times and pretty good response times in those sort of intermediate suburban settings that are very close to the downtown. So most of the vehicles are circulating in here. But when you cut down the geofence to a much more reasonable and practical in the short-term service area for those SAV fleet managers, you get much more consistent wait times. And then when you cut it down even further to just the city of Chicago. And of course, I think whichever fleet managers start to operate here, they probably will have a smaller geofence than that entire city, which has this odd little piece out here that actually technically belongs to the city. So And these traffic analysis zones are interesting to me too, because they're, very grid oriented and, simple in shape, which is kind of nice. So very consistent shape and very low response times. So averaging less than 5 minutes when we go into a City of Chicago service only. And so that was nice to see that it didn't really matter too much where you lived, unless you really lived in the boonies, that you would get pretty decent response times. But it's easier for the service, of course, to circulate those vehicles in a smaller region more uniformly. And another way that Murti presents the results is taking a look at these 4 geofences across the bottom. So the no geofence is the full 20 counties. And he's showing you with the red line just that ratio of population to jobs. It was done simply, I think, across zones rather than, a weighted average by what, the population feels, or it's certainly not a simple total jobs divided by, or total population divided by total jobs, because that would be closer to 2. It's usually 2 for most regions in the world. So when you average across zones, you get some pretty high numbers here because of the preponderance of suburban style or residentially oriented zones. And the empty VMT is, of course, falling when you add the dynamic ride sharing. Still not really sure what the base case is. This looks ridiculous to me to have a 40% empty VMT, but you do start to see those really high empty VMTs even in the standard SAV case, without ride sharing being permitted, and then with ride sharing, which is of course more complicated for the fleet manager to provide. And maybe if people are worried about COVID, it may not be that popular, but this is of course what we all hope to see is the dynamic ride sharing. And when we do the 20 county service area with only about 6% of the population actually choosing this mode. So that's a problem. If we could force everybody to choose it, we could get this EVMT down, but or EVKT. I certainly wish the US were on metric. It's one of the most embarrassing things for me, besides our president. But yeah, it's so I'll keep saying VMT, but of course VKT is the proportion is going to be identical here. And so ride sharing is reducing that empty vehicle miles traveled by, a good factor, maybe a third or at least a quarter or a fifth, I suppose, when we're in the city of Chicago. With the same fleet size, getting, maybe higher usage rates, because it does can reduce the cost. But we are assuming a low cost to begin with. We're assuming just 50 cents per passenger mile served, so or revenue mile, so the travel party served, and yeah, those I would ignore those white bars if I were you and just focus on these. So empty vehicle miles traveled, and especially with dynamic ride sharing permitted, is pretty low when you're serving the smaller geofences, but the bigger geofences, it starts to take off. And of course, 10% more vehicle miles traveled in the city of Chicago is gridlocking at certain times of day. And so that's why I mentioned earlier in the notes, the chat box, that, the only thing I can come up with is credit-based congestion pricing or rationing or something which would be kind of draconian, and credit-based means everybody gets the revenues back uniformly, so it's pretty equitable. So in general, we didn't provide a lot of SAVs because we weren't getting a big mode split, given some of the other modes that are out there. But because SAVs were permitted, we were seeing fewer cars being owned by a lot of the households. So there is a vehicle ownership model endogenous here. And when we did that full region, we had some pretty high average response times, and of course the high empty vehicle miles or kilometers traveled. So greatest reduction seemed to be in the urban and the suburban core with those geofencing options. And, the smaller than a 1 SAV for every 100 travelers kind of fleet led to, I guess fewer fleet vehicles needed, because the trips are shorter as you reduce the service area. So the geofencing comes down, you've got shorter trips on average, much easier to serve for each SAV. And the response times, there were some suggestions that there might be slightly higher response times as you go out linearly with the distance to that central business district. But for the most part, it was very competitive. And so I'm surprised it's not more popular for these Chicagoans at 50 cents a mile. I would think it'd be much more popular. The dynamic ride sharing also wasn't particularly popular, and so Americans are pretty spoiled. We're not very good at sharing, I guess. So this is all based on behavioral parameters for that region. And then we do get some total vehicle miles traveled savings, almost 10%, thanks to the dynamic ride sharing with the SAVs. So when the SAVs are operational, you see lower vehicle ownership, and you see, this maybe because you're paying per mile, you might choose destinations that are not as far away. And of course, you have that mode split. Chicago's got great transit in many parts of Chicago, but not that whole region. And so you are cannibalizing some of those trips, as some of our European colleagues were saying. The second paper I want to talk about is where we aggregated stops, and we wanted to do it with Chicago, but the code kept changing because we're working with Argonne National Lab, so we had to lock down the code, and we went to this tiny town where they also had a nice model set up for Polaris. And that's, a terrific model that Murti has been contributing a lot of code to over the last couple of years. And this town is only 74 square miles. I think that might be, maybe 200 square kilometers approximately, and, only 120,000 residents in this sort of county, I guess. And so we scaled up the population to make it look more like a downtown Chicago, but we kept this single geofence, a pretty small region. And we looked at all of the origins and destinations that we had in that activity-based travel demand table of trips, and we started picking spots to have a good bus stop, basically. It's an SAV stop, so it's a pickup and drop off, PUDO stopping point, and that's what those red dots are. And they are, in this case, no closer than a quarter mile, which in metric is about 400 meters, so you probably wouldn't need to walk more than about 200 meters to serve your trip, is the idea. And there was, an aggregation algorithm behind this that's in that paper at my website. And as we scaled up the number of trips, we shifted them, of course, in time and a little bit spatially for their true origin and destination, but we still stuck with these pickup and drop off stops. And Polaris is, moving all of these people for 24-hour days is the typical simulation. And we also had other stop spacings. So we had wider stop spacings as well. And we scaled up the trip intensities because Bloomington's kind of a quiet town. And so it started to look like a major city with millions, at least 1 million people living there in this small area. So I guess it was about 5 million people living there because we had about 15 million person trips per day, which is a fair number of people per square mile. And then the travel times rose too. There's more congestion. We also had to kind of expand the road network to make this, possible. Otherwise, it would absolutely be gridlocked. And we scaled up the fleet so that we had about each SAV serving 70 person trips per day. These are not really long trips. Remember, it's 74 square miles, so it's about 7 by 10 miles. And so you're not going to have a 20-mile trip in this region. So some of these common American trip distances are not permitted in this region. And so that's why they were serving quite a few people each day. And we were only, letting them be matched to SAVs in this case if the wait time was going to be less than 10 minutes because it is kind of a small region. So we assumed everybody was willing to use dynamic ride sharing if it was competitive. And that definition of competitive means, you're not going to end up waiting more than 5 minutes extra versus a privately called SAV, or add 5% delay time for some of those congested trips, even in that small region, that could sometimes exceed a 5-minute rule. And then those pickup and drop spacings, we did allow them to do address-based, so door-to-door service, and we compared it to that quarter mile I was talking about, and then a half mile. So a half mile is about 800 meters, so you wouldn't generally be walking more than 400 meters to get to that stop. And that helps pool trips together, of course, and it simplifies, the stopping and then having to move to grab a person. So the people come to you a little bit, which speeds things up, but it does require some walking on the part of Americans, which hopefully will reduce those waistlines and improve those heart strengths. So we live a little bit longer. We saw about just 7 to 8%, similar to Chicago choosing the shared autonomous vehicle, so not super popular. And depending on the simulation that we were doing, you know, we had some walk bikes, and these percentages I think change depending on that density of trip making, because there is that endogenous feedback to travel times and costs. And when you do it without the ride sharing permitted, and we do it door to door, so there's no pickup and drop off stops identified. The SAV is only serving about 65 trips a day, so still a lot, but not as many as when you liberate these two attributes. And lots of distance in that. So it's a pretty long workday, which was surprising to me. I don't usually expect SAVs to be traveling this much, and a high empty vehicle miles traveled. So by enabling the ride sharing and those aggregation of stops, we were able to get that empty vehicle miles traveled down. What about 2 to 5% lower empty vehicle miles traveled as we increased the density? So we made it look like a real city, an interesting city, not Bloomington, Illinois, but something more like Chicago or Austin. So 5-time might look more like an Austin, and a 25-time density might look more like a Chicago central area. And then when we added ride sharing, but not those stop aggregations, we got that bump in the trips served per day. We got the empty vehicle miles traveled down, thank goodness, under 20%, which for me is kind of a cutoff. So I always advocate when I'm talking to policymakers, not a bunch of double E's, but policymakers, that 20% really should be the limit on empty vehicle miles traveled, but you can get credit for ride sharing. So your fleet might actually travel a little bit more than 19% empty. And of course, I do advocate for road tolling, but with the revenues returned to the residents of the region, which is the tricky thing about credit-based congestion pricing. Of course, the technology cost is also an interesting issue, but deciding who gets the credits is the only tricky thing, I think, really about that policy. So I'd be curious if you guys have any thoughts on that. And then, you know, slightly lower VMT being added by the SAVs, but there is some additional wait time. And you can imagine part of that is going to be, I guess, offset by the savings that you get by sharing your ride. So Uber and Lyft offer about 40% reduction in cost if you do share your ride, which is kind of nice. So when we added the stops, we added those pickup and drop off stops that we aggregated in space. You got total VMT of that fleet, I think, and maybe for the region, I'd have to ask Murti and Haunan if what they meant here, but it's about 2%. And the savings, you know, on the SAV VMT, I guess, so that was the total VMT for that region of Bloomington, and then the SAV VMT maybe at 10 to 20%. A reduction as we increase the density versus, you know, from the stop aggregation. And this is one of the pictures they created for total vehicle miles traveled in the region. And you can see these are small percentages because this was not a big mode. So we didn't force people to take this mode. It was about a 7% mode split to SAVs. And as we increase the population density 5 times or 25 times, you see that VMT falling, which is nice because that's kind of important. That's the grid locking we were talking about earlier. And a lot of it is coming from those shared rides and those SAVs not having to turn around to go pick up somebody at a different address, but, you know, stay idle there for a second while a new passenger maybe enters at that station. There's also the average vehicle occupancy. So AVO is how many people on average are in each of those vehicle miles traveled by the SAV fleet. And it's you know, wavers between 1 and like maybe a 2.2 in the afternoon. So that's when the fleet gets busiest and it makes more sense to share rides. And regardless of whether you have pickup and drop off stops aggregated, you're still going to kind of max out at about 2.2 and only at that time of day. So on average, you might be averaging a 1.6, let's say, which is better than a 1. And it does highlight one of the issues I have with our model so far. We are not letting people ride together in parties of 2 or 3 or 4, which is unrealistic. But so I keep asking my team, my awesome students, to remove trips and just put people together, because it shouldn't be one person it should be like 1.25 on average here within the city of Austin or Chicago. So their min is 1, it should be higher. So that 2.2 will also go higher, I think, once we have real travel party sizes. And it's the midday that really benefits. And from that walking, of course, a lot of people do not like to walk. Some people cannot walk. And if even you and I, as healthy as we are, carrying a lot of gear or in a rain or, you know, intense heat as we have here in August in Austin, you know, that may be hard. But if they were willing to do it, you would pick up some fleet savings or, you know, VMT savings and certainly higher average vehicle occupancy, particularly in the middle of the day. And so the stop aggregations really do help force the kind of the sharing or facilitate the sharing and avoid some of that empty driving, especially at the off peaks. And it seems to be, you know, a wise strategy. It does maybe reduce the attractiveness of the SAV in certain ways, but the response times do get better once you get to the stop, because there's already vehicles generally waiting there from previous drop-offs. And so there's kind of a trade-off there. The takeaways on this paper is, you know, ride sharing does help lower that congestion, but we're not positive how people are going to respond to it. I think in the Chicago region right now, almost half of the ride sharing cases, I guess in 2019 for the data set that we have, they asked for the shared option and they didn't all get matched, but they did ask for it, which is nice to see. And I think in San Francisco, it works really well. Here in Austin, it's very hard to match people. There's just not enough people using the ride hailing apps. High parking prices, we certainly can increase that, although with SAVs, we're probably gonna have, you know, excess parking in the downtown, and you could see parking rates fall quite a bit. The stops, the aggregation of those stops certainly increases the vehicle occupancy and lowers the vehicle miles traveled, but I think Haunan and Murti assumed that there was no disutility from walking, which is, you know, a big assumption, because usually walking is quite a bit harder than sitting in a vehicle per minute traveled. And you can get some pileups of these SAVs at these stops. So in certain locations, you really need a place for them to queue, sort of like taxi stops at hotels. And link characteristics can also be kind of important for the stop placement. So just like bus stops are often placed in high visibility areas where they have space to put benches and some protection from the elements, you know, that also affects, I think, the stop location versus the algorithm that we used. So third paper, we're going to take you to Minneapolis, St. Paul. This is called the Twin Cities because we've got these.
Sorry, yes. I need to ask you to wrap up, otherwise we will not have time for discussion. I apologize for this.
No problem. Did Christo eat into my presentation time? Anyhow, this is a mid-sized region, I guess, a lot like Austin. And what we did is we added parking lots where the curbs were getting too busy. So around the region, it's like a 7-county region, but about 134 lots. And then this is the Twin Cities, so Minneapolis and St. Paul. You can see those lots as we zoom in. And if they're not allowed to idle there. So as soon as they drop off that passenger, they have to get out of there on those locations. So maybe 200 locations were restricted. And so it added some vehicle miles traveled. So we wanted to look at that. It added the work time for the vehicles as the vehicles were operating longer. It cut into that ride sharing. And it increased wait times. So in case you're interested in that kind of thing, we did it with different fleet sizes and, you know, with and without ride sharing. And we also geofenced differently to take a look at that. But one interesting thing, and we sort of saw this in Chicago, is similar response times across that 7-county region, regardless of where you lived. So that was interesting. Sorry to put you guys over on time. Are there any questions for me in the chat box? I'm not able to see it so easily.
Thank you, Cara. I guess, let's see, any question? Otherwise, I guess we can move the questions to the final discussion. Thank you very much for giving us such a broad and detailed overview of these very interesting papers. Perhaps I can ask already Stephen to share his screen, because we are a little bit on delay, and delays accumulating slowly. Stephen, are you there? Yes.
I am here, and
great to see you.
Nice to see you as well.
So let me quickly introduce you. Stephen Zoepf, he's the Chief of Policy Development for Ellis & Associates, where he helps guide the development of open source software products for cities to manage modern transportation systems. And really excited about your talk today, which will be about sustainability in transportation and methods to measure it and improve it. So having said that, thanks for joining, and the floor is yours.
Awesome. Well, thank you so much. Can everybody see me, hear me, see my slides? Excellent. Yes. Wonderful. So I'll try to go quickly in the interest of time. I'd like to get to some of the interesting discussion here. I just wanted to start with a very simple definition of sustainable transportation. I think this is a reminder for all of the people on this call, but I'd like to do it anyway. Simply to remember that sustainable transportation is not just about environmental outcomes. Sustainable transportation, truly sustainable transportation, includes multiple different dimensions. Obviously, environmental sustainability is near the top. That's something that we commonly associate with that word sustainable. But there's also economic sustainability, in other words, vitality, economic development. And obviously in the long term, these services can't be sustainable if they're losing money. And also, of course, the third dimension of sustainability, equity, or social sustainability. So this is a definition I borrow from Joe Sussman at MIT, one of the late great transportation policymakers of our time. So again, the 3 E's definition of sustainability: environment, economy, and equity. So within this context, I also wanted to remind you of something that I think that all of you are also familiar with, which is that mobility is shaped locally and regionally. It's a highly heterogeneous system. And I just wanted to cite a few examples of that. In Michigan, you actually make left turns by going right and then making a U-turn. That's known as a Michigan left. A lot of people aren't familiar with that. In San Francisco and some places, you have transportation modes that don't exist anywhere else. In San Francisco, you have these cable cars with unique operational domains and characteristics. In Massachusetts, every single construction site has a uniformed police officer present. That's something that's not common in almost any other city. And one of my favorites, I'm actually here in Mexico right now. In Mexico City, you actually have bidirectional roundabouts. So sometimes traffic moves counterclockwise, and sometimes traffic moves clockwise in roundabouts, depending on the phase of the light. So the other thing that I wanted to remind folks of this group about is just how fast mobility systems are changing. And I think the easiest way that I've found to compare that is to compare the adoption of mobility services to the growth of McDonald's in the United States. So just as a reminder, McDonald's took about 10 years, about a decade, to sell a billion hamburgers. But it only took Uber about half that time. It took Uber about 5 years to sell 1 billion rides. And it was just 6 months before they went from their 1 billionth ride to their 2 billionth ride. And the former CEO of Uber, Travis Kalanick, used to like to brag that 2 billionth ride, in fact, was a 174-way tie. And the reason it was a 174-way tie was because 174 people started a ride at exactly the same second, and that was that 2 billionth ride. And if we think that adoption is fast, then in fact, micromobility has grown even more quickly. So these systems are really growing very, very, very fast, and it's important to keep in mind just the scale of these systems. And what that scale is in fact leading to is, in some cases, hostile relationships between those mobility systems and the cities in which they operate, or the regions in which they operate. So just a few headlines for you from recent years: Bird suing Beverly Hills over its ban of motorized scooters. Uber suspending Vienna operations after a court injunction. We're seeing similar debates play out in cities like London as well, and in fact in the entire state of California, over work classification. We're seeing issues like this situation with Waze. So this was a headline: suburbs finally figured out a way to get rid of pesky drivers on Waze shortcuts. And in fact, that photo that you see there, if you can't quite read it, it says, "Expect delays, don't trust your apps." That's in fact a rolling sign that was in place in Livermore in the Bay Area. So one of the things to keep in mind is that a lot of what regulators have done to try to approach these new systems is simply to limit scale, to say a pilot can be operated in a very small region of the city, or a pilot can be operated with a very small number vehicles. And I think this is actually not an effective way to address this contentious relationship for a couple of reasons. But first of all, changes to traditional transportation systems take decades to unfold. Just look at California high-speed rail, which was approved in 2003, has faced a very rocky set of arguments in the public domain. And even if everything were to proceed as originally envisioned, it wouldn't be operational until 2033. So 3 decades for a system like that in the traditional domain to unfold. And in terms of scale of new mobility systems, cities need to allow new mobility systems to scale to give users a vision of the future. I think that happens for a number of different reasons. First of all, in systems with high fixed costs, you really need the scale in order to allow these systems to actually function properly. Second, one of the things that is really required for these systems to grow is widespread availability. And in order to have widespread availability, what you really need is to have these devices or have this service available disproportionately high numbers across the city relative to the number of users at the outset. And the problem that this creates is that regulators really, they're tasked with protecting citizens. That's their responsibility above all else. And if you have a system, a new transportation system like scooters or like ride hailing, where you really don't fully understand the risks, if you allow these systems to grow at unbounded scale, effectively what that would mean to a regulator is that you're allowing an unbounded risk to face your population, which would be an abdication of the responsibility of the regulator. So we wrote about this about a year and a half ago, and what our conclusion was is that in order to allow these systems to both grow and flourish and to show some of the potential that they would bring, you would need to let them grow in unbounded scale, but with very fixed time points about how the effects of these systems ought to be evaluated. So let them grow in scale, but limit them in time with very fixed objectives. So one example of a social impact of new transportation systems is simply to look at the opportunity of ride-hailing to reduce drinking and driving. So Washington, D.C. recognized that this was a possibility, that you had an opportunity to make it easier for customers that were coming out of a bar or a club after a few drinks to get into a shared vehicle and make it harder for them to get into a personal vehicle. And so one of Washington, D.C.'s approaches to try to do that, in fact, was to remove parking from Thursday night to Sunday morning in a section of the city, DuPont Circle, where there were a lot of clubs and bars, and allocate all that parking space to pick up and drop off zones for taxis and ride-hailing services. And initially, what the objective was to try to figure out whether they could encourage more people to use a shared vehicle rather than a personal vehicle. Now, unfortunately, what you find out is that, and this is a different study from 2019, is that what you see as an improved opportunity to improve social outcomes isn't always necessarily manifest as social benefit. So in fact, these researchers discovered that in the years since Uber was introduced, what they saw was an increase in alcohol consumption. So where there's an opportunity to increase social welfare, there in fact was an increase in irresponsible behavior. Average number of drinks increased by about 3%. Incidence of binge drinking increased by almost 10%. And in fact, incidence of binge drinking where there was not public transit availability increased almost 20% in this particular study. So again, what we're seeing there is just because there's an opportunity to improve social outcomes doesn't mean that we actually will improve social outcomes. So one other dimension that I'd like to look at, and this is a study that I was involved with personally, is looking at whether our transportation system is equitable. And this was a study I conducted with Don McKenzie at UW and one of his students at the time, and Chris Knittel at MIT. And one of the things that we were looking at was with the emergence of ride-hailing, we wanted to understand whether ride-hailing was improving access to transportation, so addressing historical inequalities in transportation systems like the difficulty that minorities faced getting taxi cabs, for example, and understanding whether the emergence of ride-hailing as a replacement to taxis was actually resulting in basically correcting this historic discrimination, or whether it was just hiding this. Now, as part of our study, what we had to try to understand was all the different pathways by which a service like ride-hailing might actually impact equity concerns. And we identified 4 different ways that this could conceivably happen. First was before the ride in terms of where the systems operate. If this is a driver-centric study, where does the driver choose to drive? During the requests, as the requests are being dispatched from passengers to drivers, how do the drivers respond to those requests? Do they reject them? Do they cancel them? And then during the ride, how is the service quality? This could be something as simple as the manner in which you interact with a passenger, but it also could be something that has a little bit more quantifiable elements, like the route that you take, for example. And then finally, after the ride, the feedback mechanism. This is a cornerstone of the peer economy, is providing feedback both from the driver to the passenger and the passenger to the driver. And we identified that that was one way that discrimination might manifest itself. And in fact, what you see is at each of these stages along the process, there is actually information that's available to the decision maker, the driver in this case, that could enable them to discriminate if they chose to do so. Neighborhood demographics or hearsay about, let's say, the safety of the neighborhood, the makeup of the neighborhood. During the requests, the location of a request might give you some clue about who that person might be. The first name of that person could be enough to indicate to you what the race or gender of that individual might be. During the ride, obviously you have the name, but now you also have that passenger in the car with you, and the interaction with that passenger would allow you to understand their race and their gender potentially. And then after the ride, obviously you've had that interaction with that passenger. Now, what we discovered in this ride, in this study, was in fact that drivers were using those characteristics that in a way that affected their behavior with the passengers. This was an audit study, and the link you can see down there below. Essentially, what we did is send passengers out to get 1,500 rides with different names. And what we discovered was that the cancellation rate on the passengers that used Black-sounding names, stereotypically Black-sounding names, the cancellation rate was 2 to 3 times as high for those passengers. Now, interestingly, in the places where the service quality was high, there was a lot of density of rides that didn't have a strong impact on the wait times that these customers faced. So one of the ways that you can mitigate potentially these discriminatory elements is by just increasing the density, increasing the service quality of these systems. So what are some of the challenges that face mobility systems today? Well, I think a number of the other speakers have identified some of these already, so I won't spend a lot of time on these, but massive externalities, positive and negative, affecting things like congestion or emissions or safety, as some of our other presenters have mentioned. We have a market structure in many cases that's approaching an oligopoly. In many cases, you just have a handful of providers on a given mode for, let's say, ride hail or for scooter share or bike share, really only a handful of providers. And this can create a problem because even if the providers individually recognize that their behavior, let's say over deploying, creating excess deadhead miles, lowering occupancy, they might be self-aware enough to recognize that those impacts are creating social externalities. They might still have an incentive to continue to engage in that behavior simply out of a relative advantage question. They want to make sure that their availability is better than their competition's availability, for example. And finally, operations that have been largely opaque to regulators and really regulations that just lag technical progress on the provider side. So what technologies do we have to solve this type of problem today? And so I just wanted to spend a couple of minutes on what I personally have been working on in the last year or so with Lacuna. It's really started with the micromobility space, and specifically, some of you may be aware of a technology called the mobility data specification. Essentially what this was a way to structure thinking around new mobility systems and to express the operations of these systems as a state machine. And so this was the state machine that MDS uses for micromobility systems. And as you can see, the green states are when vehicles are not in the public right of way. They could be being charged, undergoing maintenance, and so on. And the purple states are states where those vehicles are in the public right-of-way, whether they're on a trip, they're unavailable because maybe they're damaged and not been picked up yet, they're available, or potentially they've been reserved by a customer. Now, one of the things that not everyone knows is that the mobility data specification is in fact bidirectional. Many of us have used MDS, let's say, to create visualizations about when and where scooters are operating or shared bike systems are operating. But what the mobility data specification also does is give cities the capability to write policies digitally. So you can see here on the left, this was a plain English policy that Los Angeles Department of Transportation wanted to deploy last year. This was for a temporary event, a ciclovia event, where they wanted to close a specific section of road for a temporary event. And during this time, they wanted to limit the types of activities that mobility providers might be engaged in that particular region. Now, what you can see on the right-hand side is the digital expression of that policy. This is basically a JSON object that's been formatted in the rules required by MDS, and basically allows that policy to be expressed digitally attached to a GeoJSON object that then providers are capable of ingesting and implementing. Now, these simple rules let you create pretty expressive policies. Imagine you could have a citywide policy that expresses the maximum number of vehicles that are allowed in a specific region. But on the other hand, you can also create subsections of that city where you would allow additional vehicles. These could be an underserved area, or an area where demand is particularly high, for example, a tourist area. So just wanted to show you an example of where, in fact, that's actually been applied in the city of Los Angeles. This is in the case of Venice Beach. So Venice is one of those cities that is a popular tourist area in Los Angeles. What the city was observing, in fact, were vehicle deployments that in some cases were exceeding 2,000 vehicles per square mile. And this is really creating lots of headaches for local residents, where these vehicles were basically being dropped on street corners, bus stops, in some cases being dumped into the canals. And so the city created a vehicle cap, as well as a few other policies, speed limits near the boardwalk, for example, no ride zones. And what they observed was, in fact, that after the implementation of this policy, they were actually able to observe measurable differences in provider behavior. Very little riding in these no ride zones. People could still Flintstone them along, but they wouldn't have the motor active, for example, as well as more regulated deployments and a smaller number of vehicles consistent with the objectives of that policy. So in addressing this community of researchers, how can this community of researchers help? Well, first of all—
sorry, could you wrap up in about a minute?
Yes, absolutely. I'm almost done. So
okay,
first of all,
thanks.
Remember that transportation systems have created or worsened, exacerbated many of society's inequities today, and we have a responsibility to address them. Second is to think creatively about how we can write equity-enhancing policies that use objective functions or constraints, and recognizing that these systems impose both costs and benefits. And finally, to engage with groups like the Open Mobility Foundation that are moving these efforts from theory to practice today. So thanks for your attention. For those of you that use WeChat, that's me on the right. For those of you that's Twitter, that's me on the left. Thanks, everybody.
Thanks, Stephen. Very interesting talk indeed, which enables us then to move for final discussion. So I'd like to thank all the speakers, and I'd like to encourage them to now share their webcam for our final discussion. So in these talks, we have kind of seen that everyone is kind of striving towards combining new technologies to achieve sustainable mobility. We've also touched upon human in the loop aspects, so kind of trying to simulate what will happen if, and I've seen also Stephen pointing out the importance of this, of the importance of enabling these scenarios to scale up, and of course simulations would be a very good way to test it. And also underlining the importance, how important it is to have a cooperation between industrial and environmental and governmental stakeholders, whereby different timescales somehow need to come together, right? And then at the end, also the importance of having some kind of not only a sustainable deployment, but perhaps for us, the engineers, the scientists, a human-centered sustainable research and development. So kind of to combine innovation and humanism. But these are just some keywords I'd like to throw there. But perhaps, Steven, you talked, and I'd like to start with this question. You talked about the importance of experimenting, right? And I think one big experiment we were forced into in this period is the lockdown situation and the arrival of this pandemic, which changed significantly the scenario. I heard Christos talking in another workshop talking about how nice it is to drive in Boston nowadays. So perhaps, Steven, what are the lessons? Are there lessons to be learned from COVID and from the situation, of course, from the epidemiological side? And how can we avoid a non-sustainable back to normal? So what should we do in your opinion?
I mean, it's a really interesting question. And I mean, there are all sorts of dimensions to that, right? Around, I think equity for me is a big one. I think that we're seeing that a lot of the people that are forced to continue to expose themselves to COVID because they have essential jobs are overrepresenting minorities, women, people with low incomes. And so, you know, one of the lessons for me is that we really need to be taking more steps to protect these populations. And that's true both as researchers and policymakers. That's the first thing. I think, you know, the second thing is you're absolutely right. There are, I think there's kind of a heaven and a hell outcome here, right? And the heaven is where we have maybe a pullback from public transit out of a fear of density, but we see more active transit, bicycles, for example, a lot of resurgence in bicycle. I think there's like in the United States, there's a 300 or 400% increase in bike sales this year. It's pretty crazy. And you know, of course, the alternative is the hell scenario, which is everybody's getting back into their private cars, acquiring low budget used cars that create more emissions problems. And so I think the question will be, how can we create the proper set of incentives to nudge people more toward the heaven and away from the hell?
I want to volunteer some related information from the Boston area. So in April, we were able to conduct an experiment as an unintended consequence of COVID-19 that we would have never been able to conduct otherwise. The experiment is, how much would pollution be reduced by if you cut down the level of traffic by, let's say, 60 to 70%, which is roughly what happened between March and April. And this is an experiment that was conducted by accident in Boston. And what came as a huge surprise to me is that within 2 weeks, the level of pollution dropped by 40%. I would have never expected that. I would have said, well, you know, if in 2 weeks, in just 2 weeks, it drops by 5%, I would have been very happy. So we've learned something. We've learned that by, say, dropping the level of traffic by half, we can almost at the same time eliminate or reduce pollution by half. I think this is good news. How exactly we can sustain that, I have no idea. But it's certainly something to keep in mind.
Did you have more wind in April? Were there any meteorological conditions that also would have contributed to that?
Not that I know of. It was a pretty normal, by all standards, early spring. Nothing unusual.
Yeah, but anyway, there is a question by Carlos for Steven. Carlos, are you still there?
Yeah. Yeah, I can read. Just was curious about the Venice Beach case on what were the impacts on the demand side. So especially in terms of unmet demand or even additional burden due to mode changes, given that no scooters were available.
Yeah, that's an interesting question. So one of the challenges that you have is that there's certain elements that are considered kind of basically walled from regulators, and so For instance, through MDS, the regulators don't observe things like app openings. They don't observe, vehicle searches, for example. So there may, in fact, be unmet demand. I think you're absolutely right. What you can observe a little bit, I think partially gets at your question, is looking at the utilization rate of the vehicles, the number of trips per day per vehicle, for example. That will give you some insight into that. But I think there are limitations to that, and we didn't directly observe things like vehicle traffic that would have let us kind of look at mode shift, for example. But there have been other examples where cities have implemented new policies, protected bike lanes, for example, and you can observe a change in behavior based on that. So there's a protected bike lane installed on Main Street and Spring Street in downtown. And what you observed, in fact, was a collapsing of the traffic from the adjacent roads onto the road that had the protected bike lane available. So some dynamics you can observe, others you can't.
So if I were to summarize the workshop, the first half of the talks focused on advocating for policy regulation mechanisms, where the second half of the workshop proposed and evaluated different types of policy mechanisms, such as geofencing. So I wanted to ask the panel, in your mind, what is the lowest hanging fruit? We talked about the geofencing, we talked about the credit-based congestion pricing, but in your mind, what is the lowest possible hanging fruit that policymakers should really consider for implementation?
I'm going to say something which is not that friendly.
Yes, please.
Taxes, but that's not probably the way that we are talking here. I mean, so if we talk about traffic management, right? The economists had the holy grail of congestion pricing. It never came out to be true because I don't think today, for technological reasons, but mostly for political reasons and acceptance. On the other side, now we have a bunch of stuff coming out on the technology side, promising all the benefits to tackle traffic management, but still, I'm not sure that it's going to be accepted from the travelers and the users without carefully accounting for the penalties that they will face. So even if we let the entire system operate and make the decisions for the travelers, it will not be without some cost that needs to be carefully accounted for. And here we have again the same problem on how will these mechanisms come into play with the acceptance of the users. So of course we can force, and COVID was an example where people would force to change their travel patterns. And in probably a few months and a couple of years, we'll be able to have some estimations of the burden that it took, despite, of course, some gains that, like Christos was pointing to. But it's not clear to me there shall be one low-hanging fruit that should be implemented. Clearly, the advantage on the automation and on the technology that is coming up is that probably some few solutions have to started to be deployed at the same time, then slowly started to see the benefits. And we talked into a few of them: integration with public transit, incentives, eventually some control schemes at area levels. Both Karen and Steph mentioned them. And of course, on the operations side and all the algorithms, all the efficiency that comes into play. And I think here there should be small, increment benefits in all of these.
Anyone else?
Well, that's a difficult question. It's as they say, it's hard to make predictions, especially about the future. But my sense is that technologically speaking, there are more lower hanging fruit because technology is moving pretty fast, and there aren't that many human factors involved. Where things get complicated is when you have to have policies made, and some of you talked about those aspects, and I always admire those of you who get into those problems because they are so hard to deal with. So my experience in dealing with people of the city of Boston is that the technological side is relatively easy. You offer these great ideas, and I've done it personally, not just with autonomous vehicles, or with things like smart parking and what we call the street bump system, where you could sense bumps on the road and therefore detect where potholes are and then send all the public works vehicles there. I mean, really great ideas technologically, but they're all for naught if you cannot get the right policies to be made. And those are really hard. Whether it's taxation, congestion pricing, actually, I think is a fascinating problem that seems like a low-hanging fruit to me, but it's not. I'm convinced it's not, at least in an environment like the one we have in Boston. I have no idea how it might be in Zurich or in Denmark or wherever else. But that's my general sense.
I think that in order for there to be effective policies, you need to start with a shared understanding. You can't have two different groups that have an entirely different view of the world and then have them try to negotiate about a contentious topic. And I mean, there's actually in the policy sphere, this is called a boundary object, right? You try to create this thing that you can use together basically as a model, so that you can have a common understanding. Because otherwise, you're just arguing about principles and philosophies.
Yeah, maybe I would go back to what Carlos was presenting about the urban topologies. And I think this can have many different answers depending on the region that we are looking at. And I mean, especially you see these very large differences when you look at the European cities and you look at the cities in the States. They're substantially different, not only topographically, but how they were designed, and also looking at the modal shares, being it more car-oriented or public transport-oriented. I think for what we didn't touch upon here is, I think none of us presented any, let's say, first or last mile services with AVs, kind of intermodal services. And for Switzerland, this is maybe something that we have to look at in order to improve the connectivity of the rural areas to the urban cores, because these are basically the areas that are basically struggling to connect to public transport services in order to reach the business locations. So they are opting out for a car service. If they had some kind of service that would allow them to approach the train lines, this would definitely help even to promote the public transport service as well. So I think that this is definitely a very important topic, and I think it is a really a regional question. It's very hard to generalize.
So perhaps a last question. Marco asked what is the lowest hanging fruit. Maybe I can ask the panel, what is the most difficult technical challenge that we are facing right now that we need to overcome to then foster more sustainable mobility means? I don't know who wants to take it.
Well, you usually want to price your users somehow or make them, congestion is not as bad as people think. I mean, crashes are worth a lot more, and now air quality is actually, we're realizing a real issue because of the particulate matter lodging deep in your lungs for many decades, and then you die early. And if you add up the years lost, it's really rivaling almost what we lose on the road. And both of those are much more expensive than the loss of congestion. So you don't want to bring in an expensive congestion fix, but I do think, Singapore is going with this Gen 2. It's basically just a phone being put on every one of those vehicles. They don't have a big vehicle fleet, and it is expensive right now. It's like $400 or more per per vehicle. And so that's too expensive. We got to get past that. But something where you don't have big gantries, you don't have cameras, also getting backup confirmation on those license plates, that's going to be pretty critical. And hopefully it'll have a lot of apps. It will pay for parking. It will pay for your soda at McDonald's or whatever. You know, it's not just going to be for your car. And it could be lane by lane eventually with 5G. It might get that precise in many settings that you could even have people shift over leftward to take a slightly higher cost, faster trip. But that money coming back for use, not just on the roads, but for these micromobility, these transit services, even maybe a kayak or something fun, but electric bikes for sure, that opens up a lot more options and really pays people to stay off the roads. And so a lot of people will cash in their credits that way, or they'll donate them to, you know, to some single parent who's working and has to spend a lot of money on the roads to hit those time constraints that he or she has with the kids. So that's one of the big things. I also think, you know, curbing that empty vehicle miles traveled is really important. And going back to your first mile, last mile question, we simulated that for Austin train stations, and at least 50% of the vehicle miles traveled on those little SAVs around those train stations was empty. So that was kind of a bummer. It didn't also, you know, grab a big mode share here in Austin, but it might certainly in Zurich and other locations.
One thing I can contribute is the in terms of challenges that Mauro brought up is the unintended consequences. What I have found fascinating is again, drawing on my experience working with the Boston people, is many technological solutions that seem wonderful and all that, and even if people are willing to adopt it, there are unintended consequences. Example, so about a year and a half ago, we were approached by the Massachusetts Department of Transportation, and they showed us a bunch of data showing that for some reason, they were observing an increase in congestion, in traffic from the suburbs into the city that did not coincide with the usual congestion hours. It would be like at 10 or 11 o'clock in the morning. And conversely, they would see also a bump in traffic leaving the downtown area later at night. Why was that? Well, it turned out that this was due to the following phenomenon. A lot of people who are retired or they don't really, they're not part of the commuting crowd and live in the suburbs, became Uber drivers or Lyft drivers. So instead of staying in their nice, comfortable suburbs, either because of boredom or because of a need for an extra income, they would drive their cars after the congestion time, so 10, 11 o'clock, and then they would congest the downtown area, and then they would leave later on. So what was also found was that the traffic in downtown Boston would go up significantly after they would show up and would go down after they would leave. Nobody really would expect that. And these were significant numbers. They were not, you know, small numbers. So here's one example. I would have never expected or predicted that. And again, maybe it wouldn't happen in other cities. Maybe it's a characteristic of the Boston area population. Who knows?
So,
No, it's
Christos,
pretty severe in San Francisco because the land is so expensive. So all their drivers are coming from low rent, which is still high rent for most of America, but they're coming from other locations, and they're driving a lot of empty VMT to get into the job site where all the trips are.
You know, that's interesting. You know, I met a driver once in San Francisco who was actually from Fresno. So Fresno, for those of you who don't know it, that's like 3 hours away. And he was actually living in his car, and he was living in his car for stretches up to 3 or 4 weeks at a time. And so it's not just a question of deadheading and miles traveled. It's also a question of, okay, these people are going to be parking and living somewhere in that urban core now. You know, I think one of the most interesting areas of TNC regulation that I've seen in the last couple of years is the California Clean Miles regulation. So this is a regulation that CARB and the Public Utilities Commission are jointly administering. They're just starting it now. And it's a regulation on CO2 per passenger miles traveled. And this impinges on ride-hailing organizations. There are a few problems with it, and we don't have time to get into them. But one of the ones that you kind of see on its face is if you limit the CO2 per passenger miles traveled, then one of the things that you're going to be doing is potentially pushing the TNC behavior towards places where there's lower deadheading. Now, what that may mean is that's going to affect where you choose to serve, right? So it could mean potentially in rural areas where deadheading is longer, you might have reduced service quality in those areas. So right there on its face, you see a potential trade-off between your environmental goals and your equity goals.
Okay, thanks a lot. I think time has come for us to wrap up. First, I would like to thank the audience for sticking around with us, to thank the speakers for the very interesting talks. We should be able to provide you on the website the PDF of your talks later on. And of course, thanks Marco for jointly organizing this workshop. And yeah, if the speakers agree, I think it was a very interesting session, very intense and you see how important these problems are. Right now, it would be nice to see how the situation has changed in 1 year, and perhaps reorganize this workshop at the next conference, if you agree. And I don't know, Mark, if you want to add anything else.
Well, I thoroughly enjoyed the discussion. I think it will be wonderful to keep these groups somehow together. So Mauro and I are considering the possibility of reorganizing this workshop in 1 year from now. This is a field that is now moving very quickly, both technologically and from a policy standpoint. And now we also have the lockdown variable that is going to play a major role. So it will be very interesting to see how things will have changed in 1 year from now. So be on the lookout for an email from us engaging you for a similar workshop next year.
Good. Having said that, I would like to thank you. Yeah.
Thank you.
And there was a question from Kara regarding special credentials to access those online files. We're going to inquire with the ITSC technology people to see how we are able to access that information. So we'll let you know.
Thank you.
Yep.
Bye, guys.
Okay.
Thank you, everybody.
Thank you very much.
Thanks, everybody.
Have a nice rest of your Sunday.
Bye. And thank you both for organizing this.
Of course, our pleasure. Thank you very much for participating.
Thank you.
Thank
Bye-bye.
you guys for the organization. Bye-bye.